Hello everyone and welcome to my channel. My name is RF and today I'm going to continue our journey in circuit analysis courses with an introduction to AC circuits. So we will now start the very important subject of AC circuits. Let's begin. So have you ever wondered why your home outlets provide AC instead of DC, or why impedances and phasors show up everywhere in circuit analysis? So in today's video, we will study the principle of operation of AC circuits, and we will go through some components that make up these circuits. And also we'll look at some real-life examples and applications of AC circuits. I try to emphasize the difference between AC and DC circuits as well. So let's begin. So we have AC waveforms versus DC waveforms. So let me just show you with the pencil. So in DC wave, as you all know, there is only one constant value of voltage. So for example, in this DC wave, the voltage or whatever is the signal has the value of 0. So in this case, we say that the voltage or whatever is the signal is a constant signal, a constant value. So we have a constant voltage or current. While in AC circuits, we have an alternating value. So as you can see, this one is the most popular waveform, known as a sinusoidal waveform. So this is a sinusoidal voltage or current. In a sinusoidal wave, or in general, in an AC waveform, there are some characteristics, some features of the signal. The most important ones are mentioned here. We have peak value. So as the name confers, the peak value is like the max value. So the peak value of this wave is over here. And by peak value, I don't mean just the max value. The peak value can also be the minimum value. So this wave has the maximum value over here and the minimum value over here. By the way, the maximum and the minimum value are the same. I mean, the absolute values are the same, just the sign of the value is opposite. We also have RMS value that I'm going to explain in a little bit later. And the representation of a sine or cosine waveform is, as you can see here. For example, for a sinusoidal voltage, we say V of t, because the voltage is a function of time, is Vm sine of omega t plus phi. So Vm is actually the peak value, and omega is the frequency, which we're going to just learn a little bit later, and phi is actually our initial phase. I'm going to just say initial phase. All right, let's see what each one of these components are. We start with the most important concepts in AC circuits: frequency, period, and amplitude. So if we consider this waveform as a voltage or a current signal, the frequency, which I'm pretty much sure you heard a lot, some of you might be masters in this realm of study, frequency is the total number of cycles in the unit of time. And by unit of time, I mean 1 second. As you can see, it's shown here. So how many times a wave repeats itself in 1 second denotes the frequency of that wave. So for example, in this picture here, this wave repeats itself 3 times, as you can see, 1, 2, and 3, and all these things happen in 1 second. So there are 3 events of this wave appearance in 1 second. Therefore, we say that the frequency of this wave is 3, and the unit of frequency is hertz, and we show it with Hz. This is an indication of hertz. On the other hand, what is period? To put it in a simple word, I simply say period is the inverse of frequency. So if the frequency is the total number of cycles in the unit of time, the period would be the time that it takes for a wave to complete 1 cycle. So if this wave repeats itself 3 times in 1 second, can you say how much time it takes to repeat just 1 cycle? Yeah, that's easy. That would be 1/3. So this is the indication of period. We show it with capital T. It's 1/frequency, which we show it with F. So if frequency is 3 Hertz, the period is 1/3. And the unit of period, as obviously as it is time. So the unit of period is second. So the period of this wave is 1/3 of second. And the frequency is 3 Hertz. What is amplitude? Yeah, I've already mentioned that amplitude is the max value of a wave. So this is the amplitude. Or if we consider the absolute value, I can also show these minimum peaks. So this value from 0 all the way to the peak point, whatever, let's say it's 5, that is the amplitude of this wave. On the other hand, I can show it from negative side. This is also the amplitude. So this wave extends from the negative amplitude all the way to the positive amplitude. Okay, let's continue. Now let's consider another important concept in AC signals, which is RMS value. Actually, RMS, that you might have heard or you may not, is an abbreviation. It actually means the root mean square value of a signal. So R is root, M is mean, and S is square. So in total, we say RMS is the root mean square value of a signal. If we apply them one by one to our AC signal, so considering this waveform here, what is the RMS of this waveform based off this definition? It's root mean square. So the root means the square root, like this. And the mean of the square value. The square value means Vt square, or whatever is the signal. And the mean is 1/period, and the integral over that period. So this formula represents the RMS value of this waveform, if we consider this waveform as the waveform of Vt. All right, so the AC wave as our voltage or current signal has an RMS value, which is shown with this formula. And if we suppose the period of wave as t, then this is the RMS value. But the question is, why RMS is important? Why do we care about the RMS value? As you can see, there are a lot of ups and downs in this circuit. So the value of this signal changes and varies over time. So because it tells you, the RMS actually tells you the effective DC equivalent of the AC waveform. I mean, if you calculate this in a real example, the RMS value would be a DC amount of this wave. And because it gives you an effective DC equivalent of this AC circuit, it is useful for power calculations. So unlike instantaneous values that we have in DC circuits, the RMS value represents the equivalent DC value of a signal that would produce the same power. Moreover, all multimeters and measuring tools that measure AC signals, they all operate based on the RMS value of the signal. So the readings on the screen of those devices display the RMS value of voltage, current, or power. It's all derived from this RMS value. And as I mentioned, the RMS value is also known as the effective value of an AC signal. Okay, let's continue. In DC circuits, we have only resistors, but in AC circuit, we have a new concept known as impedance. Impedance. So for a resistor, as you can see in this picture, impedance simply means the same. So we show it as R. But we also have other components in AC circuits that we're going to delve more into them. Those are capacitors and inductors. And these are the circuit representation of capacitor and inductor. And just briefly, I mentioned here, the impedance of an inductor is shown as J omega L, and L is actually the inductance of an inductor. And for a capacitor, it's the inverse of this value. So impedance of a capacitor is 1 over J omega C, and C over here is actually the capacitance of a capacitor. We will delve more into that in upcoming lessons. Okay, let's continue. AC power. Actually, in AC circuits, voltage and currents are not always in phase. I mean, they don't share the same harmony, meaning that current either lags or leads the voltage. And because of the existence of inductors and capacitors, sometimes the current arrives late, in which case we say it lags, or early, in which case we say it leads compared to the voltage wave. So this misalignment creates two kinds of power, as you see: real power, which is shown with P, and unreal or reactive power, which is shown with Q. In DC circuits, we only have this power, P. And as you know, in DC circuits, real power is voltage times current. But in AC circuits, we have another power, Q. Actually, real power is the power that does work. For example, heating, lighting, running motors. But reactive power does not do real work, but it is necessary for AC systems to function. Real power is measured in watts. It's not shown here, but yeah, real power is shown in watts. And reactive power, the unit is VAR, volt ampere reactive, VAR. And just want to put it in a simple way. So just consider it as a glass of beer. The best analogy to consider is beer mug analogy. Just think of a beer mug. So the beer itself is the liquid, and we consider that as So let me just show it here. So the liquid in a glass of beer is actually the real power. However, you know that we also have foams in a beer. Sorry if I'm not showing very well. So there are some foams in a glass of beer, right? That foam can be considered as reactive power. We never pay for the foam, but we pay for the total mug size, which is our apparent power. So if I want to show the apparent power, I'm going to show the whole mug of beer. So the whole mug of beer is our apparent power, and the liquid beer inside that mug is my real power, which is also known as active power, and the foam inside the mug of beer is known as my reactive power. When you order a mug of beer, you want real power, but you always get some foam, which is reactive power. So the mug size must be big enough for beer plus foam. Beer plus foam, which we call it apparent power. And we show it with S in power systems. So you don't actually use reactive power, but it's unavoidable and it affects the system. Reactive power is actually the energy that flows back and forth between the source and the reactive components, which are capacitors and inductances. In an inductor, actually, energy is stored in the magnetic field. On the other hand, in a capacitor, energy is stored in the electric field. And this back and forth energy exchange is not consumed, but it is necessary. It is necessary. And the mathematical explanation of these three types of power is as you see here. For real power, it's voltage times current times the cosine of the phase difference between these two signals. And for reactive power, it's voltage times current times the sine of the phase difference between voltage and current. And in apparent power, we don't consider that phase difference. All we care is voltage and current. And this phase difference also introduces a new concept in AC systems known as power factor concept. I just briefly mentioned it here, but again, I will delve much deeper into power factor concepts and how it affects the quality of our power in an AC system. Last but not least are the applications of AC systems, of AC signals. So we have it in power systems, we have it in motors and generators. So motors and generators, most of them, because we also have DC motors and DC generators. So like the majority of motors and generators are AC. We also use AC signals in filters and electronics, as well as antenna tuning and signal processing. Thank you very much for your time, and in upcoming lessons we will delve more into the components of AC power systems. And if you like the content that I provided today, please don't forget to subscribe to my channel and hit the like button, and this way you support me and just motivate me so I could produce more contents. Let's help everyone grow together. Thank you very much. Have a good day.